Hi. So I'm going to be discussing the structure of antibodies and the different classes of antibodies that there are. So first, I want to hit on the structure of antibody. The first key feature I want to talk about is something termed immunoglobulin domains. And antibodies are actually made up of these domains. What is this domain? The domain is generated when a polypeptide chain folds into an organized series of antiparallel beta-pleated sheets. Within each domain, these beta strands are arranged such that a pair of the beta sheets are going to form a tertiary, very compact domain. The number of strands per sheet is actually going to vary between proteins, but in general, these domains contain approximately 110 amino acids and 3 to 5 strands. Neighboring domains can be connected to each other by a stretch of relatively unstructured polypeptide chains. And the pair of beta sheets within each domain are actually stabilized with respect to one another via interchain disulfide bonds. And there's also lots of interactions happening between the beta strands themselves. What are these interactions? Well, it's actually hydrophobic and hydrophilic amino acids alternate. And their side chains are oriented perpendicular to the plane of the sheet. The hydrophobic amino acids on one sheet are oriented toward the opposite sheet so that the two sheets within each domain are therefore stabilized by hydrophobic interactions and also covalent disulfide bonds. So a major underlying concept is normally how a structure will determine the function. And I think that the immunoglobulin domain fold is like a perfect example of that. So what do I mean? Well, at the end of these beta sheets, there are actually very loosely folded polypeptide regions. And these regions are linking one beta strand to the next. And these regions can actually accommodate for a variety of amino acid side chain length and structure without causing any disruption to the overall molecule. So these domains are actually very useful because these folds are so well adapted in the antibody molecules that they provide a single scaffold onto which many different binding sites can be built, all because the antigen binding sites can simply be built into these loosely folded regions of the antigen binding domains. And that's why these domains are very useful in proteins with adhesive function or recognition, because one, the domain structure itself provides a molecular backbone, while two, those loosely folded regions can be adapted to where they will bind specifically to many antigenic structures. So that's just a bit about immunoglobulin domains as a component of the antibody structure. And the second key feature of the structure that I want to discuss is that all antibodies share a common structure of 4 polypeptide chains. And that would be 2 identical light chains and 2 identical heavy chains. So each light chain actually has a partner with a heavy chain and is bound to that partner by something called a disulfide bond between corresponding cysteine residues, and also they are bound together by non-covalent interactions. And these bonds allow them to form something called a heterodimer. The 2 heavy chains are also linked about halfway down their length by multiple disulfide bridges, while the C-terminal parts of the heavy chains also participate in non-covalent bonding interactions. So just a little bit more in depth about those chains is that they are divided into specific classes of their own. So the light chains are actually divided into 2 major classes, while the heavy chains are divided into 5 major classes. Light chains actually have an amino terminal half and a carboxyl terminal half, and this amino terminal half is actually going to be the variable region, and the carboxyl half is going to be something called the constant region, and that is the region that actually can be classified into the 2 major categories. And those 2 major categories are kappa and lambda chains, and in humans actually 60% of our light chains are kappa and 40% are lambda. And so those are the 2 classes of light chains, and there are 5 major classes of heavy chains. And those are named using Greek letters: mu, delta, gamma, epsilon, and alpha. And each of these different heavy chain constant regions is referred to as an isotope. And the isotope of the heavy chains of any given antibody will actually determine something called the antibody's class. And so before I get into showing you the different classes of antibodies, I wanted to show a diagram showing the structure of the antibody in just a little more depth and talk about that. So, what you're going to see here is that the antibody molecule forms a Y shape, like the letter Y, with 2 identical antigen binding regions at the tips of the Y. And each antigen binding region has amino acids derived from both the heavy and the light chains. You can see the light blue is the light chains and the dark is the heavy chain. More specifically, the heavy and light chains are actually both going to contribute 2 domains to each arm of the Y, with that non-antigen binding domain purpose serving to extend the antigen binding arm. The base of the Y is going to consist of C-terminal domains of the antibody heavy chain. And so you can see in the base of its Y, it's predominantly a heavy chain. So this Y structure shows there are actually 3 relatively compact regions, 1, 2, 3, joined by something known as the hinge region. So what exactly is this hinge region? Well, the hinge region is very rich in proline residues, and those proline residues make it very flexible. And because of this flexibility, the hinge region can assume a wide variety of angles with respect to one another, which facilitates efficient antigen binding. And this extended nature of the chain and the hinge region is going to contribute to the vulnerability of this part of the molecule. And this vulnerability is going to make protease cleavage possible in this region. And there's an enzyme known as papain that's going to cleave this region. And it's going to resolve the antibody into 2 identical fragments. And one of these fragments is known as the Fab region, seen up here, and the other is known as the FC region. So the Fab region versus the FC region, let's talk about that. Put it back down when I talk about that. So what your Fab region does is it's actually the region that binds to the antigen, and it's actually going to retain that antigen binding specificity of the original antibody. And your FC region is actually going to have the remaining region of the molecule, which is going to contain non-antigen binding. And more on the FC region is that it actually binds to something called FC receptors on phagocytic or cytolytic cells or to immune effector cells. So yeah, that's just a summary of your antibodies are structured into a Y containing heavy chains and light chains, and that hinge region is going to connect all those, and once that hinge region is cleaved, then it's going to break up into Fab regions and FC regions containing either antigen binding sites or non-antigen binding sites. So a little bit more on the different classes of antibodies. I'm going to turn it around and show you a little diagram I have. The classes for me give more of make it more relatable to our everyday lives and when we would encounter these antibodies. So the 5 classes are IgG, IgA, IgM, IgD, and IgE. Ig is simply the abbreviation for immunoglobulin, which is simply another term for an antibody. So our IgG antibodies are the most common, and they can account for about 80% of all antibodies. They're actually responsible for resistance against many viruses, bacteria, and bacterial toxins. What's pretty cool is that these IgG antibodies are so small that they can move across membranes. So in humans, in us, that
in a pregnant woman, these IgG antibodies can actually pass through the placenta to her fetus and provide a temporary defense for her unborn child. So that's pretty cool. And these IgA antibodies are actually present in our tears, our saliva, and our mucus. And they function to neutralize bacteria and viruses and prevent them from entering our body or reaching our internal organs. And another key one I want to hit on is IgM. These are present in our blood and are clearly the largest of the antibodies, combining the 5 Y-shaped units. Their function is actually very similar to IgG in defending against antigens, but because of their large size, as you can see, they cannot easily cross membranes. And their function is an initial attack by a specific bacterial viral antigen, while our IgGs are normally thought of as being produced in later infections, such as conferring immunity. And you also have your IgE and your IgD, and IgEs are found in basophils and mast cells, and IgD in extracellular fluid.
So there's just the 5 major classes of antibodies. And the last thing I want to hit on is that these classes can be categorized even more into something called secreted antibodies versus membrane-bound antibodies. And secreted antibodies actually have a hydrophilic amino acid sequence of various lengths at the carboxyl terminus of the final domain, while in membrane-bound antibodies, those hydrophilic regions are actually replaced by 3 other regions. These 3 regions are an extracellular hydrophilic spacer, a hydrophobic transmembrane segment, and a 3 amino acid cytoplasmic tail. And so these membrane-bound versus secretion are just other ways to categorize antibodies. And how are these different forms created? Something called alternative mRNA splicing. So that's just a summary of the different classes of antibodies and how else they can be classified. And there's also a special set of antibodies that recognize other antibodies. And those are termed the anti-Fab, the anti-Fc, the anti-isotope, the anti-allotype, and the anti-idiotype. And those are categorized based on their antigenic determinants. What is an antigenic determinant? Well, it's basically a region of an antigen that makes contact with the antigen combining region on an antibody. And yeah, so those are just different from the other 5 classes in that those antibodies can actually recognize other antibodies. So yes, that's all I have, and feel free to use my video if you want. Thanks.